you how we then can describe properties of these systems. And I chose now 3 very different examples because I want to show you in which way here these electronic structure calculations are helping us to understand these materials. So the cases I'm going to show is, first I'm going to talk about strontium titanate. This is a band insulator. It's, in principle, you could tell it's a boring system. It's not, since I'm going to show it in connection with oxide heterostructures and the presence of 2-dimensional electron gases on interfaces and surfaces. Then I'm going to talk about a completely different system, and these are, in fact, nanostructures that are created by the Fibit process. I will tell you what is this Fibit process. But the question that we pose here is, once you build out these heterostructures, which are rather amorphous, can we learn something about their electronic properties by using density functional theory calculations? And I'm going to show you here, since you have no idea even what kind of crystal structure you have there. So with the help of genetic algorithms with density functional theory, how you can get information about these nanostructures. And the third example, I will continue on the iron pnictides that Paul was presenting. And here I want to go into the question of correlation effects. So this is where I stopped yesterday. So here I will continue about showing to you how we go beyond DFT in order to describe correlation effects in materials that are, where these effects are important. So this is the 3 examples, and let me start by strontium titanate. So strontium titanate, and let's start with the bulk strontium titanate. The system, if you look at this formula, this is a perovskite, a cubic perovskite. And let's just make a counting of oxidations. So here strontium is a cation with a 2+ oxidation. Oxygen is an ion with a 2- oxidation. So if you count, you will see that titanium here should have a 4+ oxidation. So if you go to the periodic table, a 4+ oxidation, it means that titanium has a 3d0 basically band, so that it's telling you you have a closed shell system. So therefore, this should be a band insulator. And a band insulator can be perfectly described by density functional theory, as I'm going to show to you. So this is a band insulator with a band gap with 3.2 electron volts. Where density functional theory is not good at is at giving, in fact, the right band gap. So usually it gives you an underestimation of the band gap, but it's otherwise very accurate in describing this system. Now, I'm not that much interested on strontium titanate, even though this system per se is very interesting because it has a very large dielectric constant. So there is a lot of work being done right now with basically this bulk material. What I want to touch today is the oxide heterostructures. This is a field, it has been a field which has been extremely hype in the last years. It has calmed down a little bit, but let me tell you a little, basically the essence. Paul is always laughing at me because I don't say this word properly, but the essence of that was right? Perfect. Okay. Essence, yeah, I use essence, but anyway. La esencia, let's use the Spanish word. So, of these heterostructures. So the idea is the following. You take, for instance, strontium titanate, which is a band insulator, and then you grow on top of it, for instance this lanthanum aluminate. Now, what is interesting about growing these heterostructures is that strontium titanate basically is what we say non-polar. So each layer, so you have strontium oxygen, titanium O2, strontium oxygen is charged, so charge-wise, it's neutral. So therefore, we call it a non-polar. But now if you put on top of it this lanthanum aluminate, which is also a band insulator, it's however polar in the sense that each layer, so each layer has a charge. It's not compensated, so this is lanthanum oxygen, aluminium oxygen, lanthanum oxygen. So what you're having here is you're building up a heterostructure by having a non-polar system with a polar system. So you have at the interface between the titanium oxide and the lanthanum aluminate, you have a charge disproportionation. And this is what it's being called the polar catastrophe. So in fact, what one observes experimentally is that at this interface between these two oxides, you build up a two-dimensional electron gas. And the initial description of the presence of this two-dimensional electron gas was basically this polar catastrophe. So this uncompensating charge that was being localized at the interface. And there has been a lot of work about the properties of this two-dimensional electron gas, superconductivity, and many other interesting effects and phases that came out of that. But now let me go to the next slide. And let's now just take strontium titanate. And these were experiments that were done in 2011 by Santander Zero in Paris, but also Metsvana in UK. So basically what they did is, let me take again bulk strontium titanate. We cleave it, so we make just crack it and make a surface on it. And let's look what I observe on the surface, whether it's a bulk, as I was saying, it's a band insulator. So what I'm showing here is basically the RPS. So it's, what I'm showing is the electronic structure in around the gamma point. And what you see is that what they observe is metallic. So basically you see these bands here, it's telling me the system is metallic. And if you want to see it by the eye, here's the sample. And basically the sample, when you go into, so when you cleave the sample, you observe basically this black, and a black sample is telling you you have a metal because it's absorbing. So there is no gap there, so it's absorbing basically the light. So you are having here electrons that are producing transport. So where does this come from? I'm not having here this building up of the heterostructure with the previously case that I could take, consider this polar catastrophe. Here there is no polar catastrophe. So where does this metallic phase come from? And so this poses the question, okay, we are doing oxides here, and we know very well, if you talk with solid-state chemists, that these systems are very prone to oxygen vacancies. So that's why we came in by trying to see whether we can simulate, in fact, these surfaces by introducing oxygen vacancies and see whether we can reproduce this conducting experiment. So then we start by, now let's do DFT. So this is now the structure of the bulk, and what we want now to simulate is what the experiment is doing. So the experiment has basically a slab, so I have vacuum, and then I have here bulk, and this is my surface. So now, of course, because it depends on the percentage of impurities, of the oxygen impurities that I may have in the experiment, I have to construct different types of slabs in order to be able to take into account different type of oxygen concentration. And I'm showing here some of the slabs that we constructed. So usually you call them 1 by 1 by 12, which means basically the dimensions is 1, 1, and then 12 layers. So this is the way you count your slabs. And then you have to put, in order to do your density functional theory calculations, you have to put a large void, so about 20 Armstrongs of void, since you want to really describe here the surface states. You don't want to have then interaction of your surface states with, because remember I'm doing periodic boundary conditions, so this goes up 20 Armstrong void, and then I continue with the structure. So I do have periodic boundary conditions in the 3 directions. So in order to avoid the interaction of the surface with this one here, I have to put this void. So this is the way you practically simulate these slabs with different concentration of oxygen vacancies. And now you go and do what I was showing yesterday. So you put this crystal structure in your computer, and then you solve self-consistently the Concham equations by using different exchange correlation functionals. So here, for instance, we choose GGA. And now let's see what we learn out of this calculation. So first of all, let me show you what we obtain if you just basically look at the electronic structure of the bulk strontium titanate. So here I'm showing these pictures I was showing to you yesterday. These are the Concham energies as basically, and here is a path in the Breuling zone, so the high symmetry points in the Breuling zone. I have a cubic structure, so this is basically the high symmetry points. And as I was telling you, this is a band insulator, and this is also what I obtained from DFT. There is a gap between the filled bands and the empty bands. And I really see here that the titanium D is unoccupied, the T2Gs are unoccupied. So okay, let me remind you, here is the titanium, here are the oxygens, and here is the strontium. So you see that the titanium is in an octahedral environment of the oxygens. So you know that the 5d orbitals in an octahedral environment due to electrostatics, they are going to split into lower T2Gs, and the T2Gs is the dxy, dxz, here they are, and dyz, and higher level EGs, which are the z squared and the x squared minus y squared. So now in this system, because in strontium titanate, all the d electrons of titanium are unoccupied, and this is what we see. And what I'm just plotting here in heavy is the 3 T2Gs, the weight of the 3 T2Gs orbitals. Okay, so far so good. Yep.
It looks like a narrowband metal at the R point.
And the what?
At the R point.
At the R point, here.
It looks like a narrowband metal.
So, good, very good observation. Okay. The point is, when you have an insulator, there is not a definition of the way you put your Fermi level. So you can, describe. Let me put your Fermi level at just the top of the highest band, or you can put also, you can have other kind of convention. You put the Fermi level in the middle of your band gap. It's just a convention. But
the DFT does tell you that the Fermi level is somewhere
filled.
In this
yes, basically the DFT gives you filled bands, and then you just define where do I put now my AF, okay, where I put my 0.
How do you know EF isn't at 4 electron volts, in which case it's not a semiconductor?
No, it's, okay, so this...
between those two.
Okay, so when you do the calculations, basically you work in Rydbergs, and you basically don't work in this. So here I'm putting my 0th here at the Fermi. When you do these calculations, your 0th is not given by that. You start from the top, exactly. Now, when I convert that in electron volts and put my 0, I just define, okay, put my 0 at the highest occupied band. That's it, and this is what you see here, okay? So Fermi level, we can only properly define it when we have a metal. Okay, so now let's go and look at,
sorry,
yes?
So what is B and C, so the difference A, B, C?
Where, A, B, C, A, B, C, A, B, C?
The panels.
Oh, sorry, yeah. The panels is, it's exactly the same band structure, and what I'm just showing to you is which bands have which character. So remember that my band structure, these Concham eigenvalues, they are well defined by the quantum numbers of my wave functions. So I have the principal quantum number, I have the orbital quantum number, I have the spin quantum number, and I have the M, so which is from the L equal to, here I am at L equal to, so D bands, which of the D bands, in fact, this band here corresponds to L2 and M, X, Y, Z, Y. This band here corresponds to L2, so I'm just showing the character of the band, the nature of the band to which L, M it corresponds. So basically it's the same band structure, but by showing the character of the orbital, okay? So now we go and do the calculations with these slabs. Again, when you do these slab calculations, as you saw, these unit cells are huge. So these are heavy calculations depending on, in fact, the approximation that you do your calculations. So if you do what we call a full potential, full electron calculations, that you include all your electrons in your system and you include, in fact, all the information of your potentials, you don't do, let's say, for instance, pseudo potentials, then they are heavy. But let me show you now, here I'm showing the density of states. So again, this is available density of states as a function of energy, and here I have my Fermi energy. Here is the bulk where I set my Fermi level to be on the top, so this is my band gap. Now here I'm just showing to you the density of states of two of the slabs where I had one oxygen vacancy per the size of the slab. And of course, since we didn't know from the experimentalists, even themselves didn't know when they were cleaving which was the surface that was there on the top, whether it was a strontium oxygen layer or it was a T oxygen 2 layer, we had to do all the calculations. So, but this in fact doesn't affect that much the results. So what happens when you put an oxygen vacancy? So when you take out an oxygen from your structure, so remember that the oxygen is an anion that likes to get 2 electrons. So if you take out the oxygen, the system will have 2 electrons more to distribute. And the question is, what happens with these 2 electrons? Do they localize around where you have this oxygen vacancy, or do they in fact produce, delocalize and give you conduction? And this is what we were trying to analyze. And basically what we find is that these 2 electrons that come from your vacancy in fact is giving you conduction. And I'm showing here a blow up of at the Fermi level where you see that now you start feeling the d orbitals of titanium. So this is of course a fraction of d, but the electrons start to feel these d orbitals, and moreover, since you are seeing here this metallic state, what it's telling me is that these electrons are forming a extended block waves. So they are producing conduction. So in principle, this is going in the direction of what the experimentalists are observing, that we seem to have in fact conduction coming from these oxygen vacancies. But now we need to be a little bit more precise. Let's investigate, what did I do? Yeah. Let's investigate now how this charge is distributed. And here what I'm showing, let me show one of the slabs that had more unit cells in the z direction, since to reproduce the experiment, for the experiment they have the surface, but then they have the bulk. Now, to reproduce the bulk, it means I have to put a lot of unit cells to have the information of having a bulk. So here there are 12 of those 12 layers, so this should be in fact long enough to have at least a hint that we are in the bulk here. And now what we looked here is how this extra charge is distributing in the system. And you see here, so I'm plotting again the density of states for these layers as a function of the depth of the slab. And of course, most of the charge is on the surface, and then it decays very rapidly, so in a Poisson way, in the bulk. So that basically you are going to expect the transport to be rather localized in this 2-dimensional surface. Okay, so this was again in the right direction, but now let's compare with experiment. So here what I'm showing is again these ARPES experiments where we have here the gamma points, and they really see these filled partial bands, which it's telling you you have conduction in the system. And moreover, here in this other experiment, they could in fact identify 2 types of bands, what we call the light bands and what we call the heavy bands. Where does all of that come from? So now when you do the calculation, what you see indeed is what you are feeling is the different nature of your T2Gs. So you have that this dxy what it corresponds to the light bands, and the D, Y, Z, X, Z are the heavy bands. So there is a very good reproduction of the experimental observations, and this is clearly telling us that this conduction comes from the oxygen vacancies. Now, after all these works, then people were going back to the heterostructures and looking, okay, in the heterostructures we have oxides, we should also have, most probably oxygen vacancies are playing a role. And there has been a lot of work done now also for the heterostructures to see the role of the oxygen vacancies. Now people grow, for instance, these heterostructures with what they say oxygen pressure to reduce the number of oxygen vacancies. However, it's very inherent, Paul can say more on that, the oxygen vacancies play an important role in oxides. And here they are, in fact, the key player in order to get this two-dimensional gas of electrons conducting. So this is an example where DFT really works well. I didn't need to put correlations, I didn't need to put very complicated extra or beyond DFT. Let's say the difficult part is to really then take care of all these slab structures and work carefully with them. So this was my first example. Let me go now to a completely different example, which is these nanostructures. So what is this focused electron beam induced deposition of nanostructures? So I have a colleague in Frankfurt who does this kind of growing of nanostructures, and it goes in the following way. So you have a focused electron beam which has energies of the order of kilo electron volts, and now what you do is you take a gas of what they call precursor metal-organic molecules. So for instance, this is tungsten hexacarboxyl or a cobalt, or here with platinum. So the idea is you have these molecules in a gas form, and now what you take a substrate, for instance, silicium dioxide, and you inject this gas of molecules, and because of this electron beam, what is going to happen is that the electron beam dissociates these molecules, and the heaviest elements get deposited. Oops, the heaviest elements get deposited. So what you expect at the end of doing this process is that you are going to have a deposit of a metallic system that then by manipulating this focused electron beam, you can just build up nanostructures in the form and the ways that you would like to have. So for instance, different lattices. So this is a lot more in the mesoscopic type of physics, because we are here at the nano level. However, one of the big issues is once I have this deposit, what can I say about the electronic properties of this deposit? Okay, one can do measurements, but I want to really understand what is the nature of this deposit. So my colleague came to us and said, can you do something on that? And I looked at that and I said, oh my God, because this, in fact, what you are building up here, this is more of an amorphous type of nanostructure. It's very disordered. And I showed to you that in the DFT calculations that we have been showing, you like to work with crystal structures that have well-defined symmetries, where you have periodic boundary conditions, and then you can use all your machinery to get out the electronic structure, but this is not the case here. So what do we do? If we want to be useful to understand something about these nanostructures. So basically what we are going to do here is the following. We have no idea which is the crystal structure or whatsoever of these systems. The only information that we have that the experimentalists can get out of their deposits is that they know well which is the ratio of the tungsten, carbon, oxygen, for instance, when they deposit this tungsten hexacarbonyl. This they know. So, okay, let's start with that. I know that I have to build up and I would call it an a crystallized approximant of my amorphous system with a certain ratio of these three elements. And what I'm going to use here is, in fact, what we call the ab initio evolutionary techniques. So basically these are algorithms, genetic algorithms that use the ideas of genetics in order to produce crystal structures when you have no idea about how these crystal structures look like. So the idea is the following. Since you don't have any starting guess from your structure, you only have the chemical composition, so you start to build up many, many structures that you are combining, cutting, basically that it's what we are calling combination and inheritance, and producing new structures. And of course, you have to use what we call a fitness solution. Here is where DFT comes in, to analyze these structures. And you can use the energy, the free energy, the enthalpy, depending on what you are interested in. So basically you have a large set of possible structures exactly with this composition, and then you with this algorithm, what you are doing is you are selecting those where this fitness function is optimized. So basically you are going to be able to go through different minima and to try to find what we call an absolute minimum in your function, or maximum, depending on which function you are choosing. So here I should mention one thing. Density functional theory calculation, I had it in my slide, but I didn't say it, follows the variational principle. So when you calculate energies with density functional theory, these are variational energies. So one thing that you really know is you can use all the properties of the variational principle. So your energies for the wave functions, the basis set that you chose, this is the best energy that you have. So therefore, that's why we can use DFT in combination with a genetic algorithm in order to find the fittest or the optimal structure where we start with then for our calculations. So basically, we used here these genetic algorithms, and we had we had many samples from them, so many compositions. Let me just show you three. These are three compositions that they had, and basically one of the questions that we wanted to answer is this composition, they were finding it's an insulator, while this they were finding it's a metal, and the question was why. So what we did then, by using this genetic algorithm, we basically tried to approximate these amorphous structures by crystalline structures, and you see it's very interesting because once you have carbon, it's clearly what carbon is trying to do. So here we have different compositions of carbons. Carbons like as much as they can to build up either this sp2 or this sp3 type of bonding, because these are where they are more stable, and this is what you're seeing here that is happening. So these were our fittest structures, and you see, I mean, we had a lot of structures. You have to do a lot of runs to really get the fittest one. So let me show you, these are the structures, and now we can calculate with DFT the electronic structure and try to see what can we say about the experiment. So here, again, I'm showing density of stage as a function of energy. This is the Fermi level. And you see clearly that we have that this structure, which was my sample 2, is insulator, while sample 3, it starts to be metallic. And this is exactly where the experimentalists were seeing this change between insulator and metallic. So what it's telling us is that in these compositions, even though the system probably is amorphous, but locally it's probably going to be organizing itself in this kind of structures where tungsten likes to be surrounded in this way by oxygen and carbon, etc., etc. So this was giving us a lot of information about these nanostructures. And now, in order to get a little bit more comparison with experiments, here what we were comparing is, these are electron diffraction intensities. So basically what I'm showing is the intensity as a function of the middle tungsten-tungsten bond distances. So this is the experiment, there is this peak here, And if I do this calculation for our structures, we see indeed that the tungsten bond lengths that we were predicting agree with those measured by experiment. So these approximants were very good to describe these nanostructures, and now start doing transport and other type of calculations. So this was a completely different type of calculation where you combine these genetic algorithms that are extremely useful. For instance, in one subject where they have been very, very useful is in describing the structures of superconductors at very, very high pressures. So you know that we were talking yesterday with Paul that I hadn't mentioned them, but I should mention them. A couple of years ago, it was possible, this was done by RMETs in Mainz, applying very large pressures, so up to, I don't know, 100 gigapascals, I don't know, 300 gigapascals. He managed to get a conventional